This fall, physicists in Italy published results suggesting that neutrinos travel faster than light, significantly faster. If true, this is really big news in physics. And of course, most scientists are reading the results with skepticism. Why, you might ask? Well, they fly in the face of the well-established and experimentally supported theories of special and general relativity. And extraordinary claims require extraordinary proof. So let's go visit the opera experiment in Italy and try to catch some neutrinos. The kind researchers looking for the Higgs boson at the LHC in Switzerland are already crashing protons into each other to create explosions of subatomic particles. And luckily, some of those particles are neutrinos, which fly straight through the Earth's crust to us here in Italy. There are just 3 things that we have to do. 1, we have to catch the neutrinos, which, given that neutrinos will travel for roughly 2 years through lead before stopping, is an ambitious task, but we can do it. 2, once we have a neutrino, we have to figure out which proton collision it came from. Imagine blowing up a case of wine bottles at night, and then having your neighbor call you up and say, "I caught a piece of glass, can you tell me which one it is?" Well, we're that neighbor. And 3, once we figure out which collision a neutrino came from, we have to know exactly what time the collision happened, and exactly when we caught the corresponding neutrino. And because the scientists in Switzerland are hundreds of kilometers away, we have to use timing signals from GPS satellites in order to synchronize our clocks. If we're off by even a microsecond, we'll get the speed wrong by 1,000,000 kilometers per hour. So that's it. Now that we've measured the neutrinos going faster than light, what next? Well, because our results are so groundbreaking, and our observations so hard to make, the scientific community wants to be absolutely sure we didn't make any big mistake. So we have to wait for other experiments around the world to confirm or refute our claim. And this could take months, or even years. So be patient. And in the meanwhile, why not learn more about neutrinos, or how GPS works? Click below to make a choice.
All right, so everything is fine except the conclusion of this. They didn't have to wait that long. They decided to replace the team with a new team of physicists. Upon coming back, you check the instrumentations and everything else, whatever your specialty is. They found a loose cable somewhere. They adjusted the cable. The neutrinos began behaving themselves. That's it. That was that simple. All right, so Einstein was right. He was correct. Some people were forced to resign. I don't know if anybody got fired, but obviously things didn't go too well for the hire. So that's what happened. Guys, they repeated this experiment. I don't know how many times, how many thousands of times. Regardless, we knew Einstein was correct because every single aspect of his theory has been tested about 1 trillion times. All right, there was no way anything with mass was going to be traveling faster than light. At the same time, I was hoping against all hopes that Einstein was wrong. I got my own motives because I was teaching a course in time travel at the art school. And I thought to myself, it would be amazing if we had something traveling faster than light. How so? What happens at the time when you start to approach the light speed? Time slows down. All right, so what happens at the time at the light speed? It stops. What do you think would happen to time if you could exceed the light speed?
Goes back.
Time is going to reverse itself. Absolutely. If you have particles traveling faster than light, they can travel backwards in time. That's amazing. I was so hoping that these people actually discovered something. I knew that it was next to impossible because imagine, guys, the AT&T or Sprint or whatever, they would offer you extra services for extra money. All right, so you could call yourself up in the past and leave a message for yourself. If you're like 50% of the time you're screwing things up, it would be nice to be able to hear from yourself, from the future, when you're about to make a decision. Unfortunately, it's not happening. Weird part of it is what a lot of physicists miss. All right, this is something that this artist did not miss. All right, this is just so conceptual. This is so beautiful. You got all these PhDs just missing the basic essence of what's going on, and this guy is right on top of it. He's talking about the results of today's faster than light experiment are coming through now. That's what he's saying. Hang on, these are the results of the next week's experiment, which means that particles traveling faster than light would travel backwards in time. This guy got it. A lot of the people did not.
Since near the velocity of light, we cannot simply add speeds. The familiar notions of absolute space and absolute time, independent of your relative motion, must give way. That's why, as Einstein showed, funny things have to happen close to the speed of light. There, our conventional perspectives of space and time strangely change. Your nose is just a little closer to me than your ears. Light reflected off your nose reaches me just an instant in time before your ears. But suppose I had a magic camera so that I could see your nose and your ears at precisely the same instant. With such a camera, you could take some pretty interesting pictures. Paolo says goodbye to his little brother Vincenzo.
Ciao, Vincenzo. Ciao.
And rides off. He's now going more than half the speed of light. He's almost catching up with his own light waves. This compresses the light waves in front of him, and his image becomes blue. The shorter wavelength is what makes blue light waves blue. Also, Paolo becomes skinny in the direction of motion. This isn't just some optical illusion. It really happens when you travel near the speed of light. As he roars away, he leaves his own light waves stout behind him. Long light waves are red, which say that his receding image is. Now, Paolo leaves for a short tour of the countryside. He experiences something even stranger. Everything he can see is squeezed into a moving window just ahead of him. Blue shifted at the center, red shifted at the edges. To a passerby, Powell appears blue shifted when approaching, red shifted when receding. But to him, the entire world is both coming and going at nearly the speed of light. Roadside houses and trees that he's already gone past still appear to him at the edge of his forward field of view, but distorted and red shifted. When he slows down, everything again looks normal. Only very close to the speed of light does the visible world get squeezed into a kind of tunnel. You would really see these distortions if you could travel near the speed of light. Someday, perhaps, interstellar navigators will take their bearings on stars behind them, whose images have all crowded together on the forward view screen. The most bizarre aspect of traveling near the speed of light is that time slows down. All clocks, mechanical and biological, tick more slowly near the speed of light. But stationary clocks tick at their usual rate. If we travel close to light speed, we age more slowly than those we left behind. Paolo's watch and his internal sense of time show that he's been gone from his friends for only a few minutes. But from their point of view, he has been away for many decades. His friends have grown up, moved on, and died. And his younger brother has been patiently waiting for him all this time. The two brothers experience the paradox of time dilation. They've encountered Einstein's special relativity.
Your chance.
This was just a thought experiment, but atomic particles traveling near the speed of light do decay more slowly than stationary particles. As strange and counterintuitive as it seems, time dilation is a law of nature.
So that's Carl Sagan from Cosmos. This was made in late 1970s, and special effects are amazing. These guys have done a really, really good job with it. It was a good summary of everything that we discussed. All right, now imagine that you're falling into a black hole, and as you start to move towards the event horizon, you're going to start to speed up because the gravitational pull becomes nearly infinitely large. So you're going to start to speed up and start to approach the light speed. And we are curious, we want to know exactly what's going to happen to you. So we're watching you live on TV. So what would we see if we're watching you live on TV as you start to approach the light speed? Your time is going to slow down. Your 1 second is going to be a minute long at some point. And that is going to be an hour long, day long, a year long, 100 years long, and 1,000,000 years long. Which means that as you start to approach the light speed, as you start to come closer to the event horizon, you're going to start to freeze up. You will hit the event horizon, and then you will freeze up on the event horizon as far as we're concerned. From your perspective, your 1 second is going to be still 1 second long. You will get past the event horizon, and you're going to keep falling into the singularity. All right, so when you start to approach the light speed, your time is going to slow down, and eventually, from our perspective, your 1 second is going to be almost eternally long. And that's the last we will see of it.
If you were watching an astronaut, foolhardy enough to jump into a black hole, at some time on his watch, say 12 o'clock, he would cross the event horizon and enter the black hole. But no matter how long you waited, you would never see the astronaut's watch reach 12 o'clock. Instead, each second on the watch would appear to take longer and longer, until the last second before midnight would take forever. Thus, by jumping into a pool, one could ensure that one's image lasted forever. But the picture would fade very rapidly, and grow so dim, that no one could see it.
As somebody disappears into a black hole, as seen from the outside, it looks as though time actually slows down, and the person becomes who's moving, at least he's thinking he's moving, he's perhaps talking in his spaceship at a normal rate, seems to slow down and ends up by being frozen in a particular position, as seen by somebody watching him from the outside. And as seen from the outside, you never see what happens after that.
The astronaut wouldn't notice anything special when his watch reached midnight, and he crossed the event horizon into the black hole. Until, of course, he approached the singularity and was crushed into spaghetti.
One can fall through this event horizon without feeling anything, without noticing it. After about a week of falling, one begins to feel the pinch and one extends longer and longer and gets slightly thinner. And, of course, one begins to get squeezed. Until one gets very long, very thin, and rather nasty. By the end of 2 weeks, one's fallen right into the center and one is, of course, dead.
Before you lose sight of the outer world, you would see things happening, and you'd see them at a greater rate, so that it would look like a firework display. And the frustration would be that although you would be able to see everything that happens in the future, it would be going so fast that from a scientific point of view, you would have no time to analyze it.
Is this guy crazy? He's talking about being able to see the future as he's falling into a black hole. How's that possible? What do you guys think? Do you think this guy's nuts?
You wouldn't be able to
Light is moving so fast and time is moving so fast around him that, in theory, he is seeing what could be considered the future.
Okay, Lucas, I'm going to give you 20 points on that one.
And eventually things would be going off so fast and it would be so explosive that you yourself would be destroyed by the explosion, and that would be the end. But it would be a very exciting way to end one's life. It would be the way I would choose if I...
All right, so the guy's nuts.
If I had the choice.
But that's a good way to go. All right, so this guy is actually talking about seeing the future as you're falling into a black hole. How's that possible? If we're watching you live on TV as you're moving towards the black hole, what happens to your time? It slows down. What if you're also watching us live on TV? CNN, if you're a Democrat, Fox, if you're a Republican, so that you can keep up with the events live on TV, what would you see? Just the opposite. Our times will speed up relative to you. Our lives will speed up relative to you. Within a second, you may be able to see about a minute of our lives, an hour of our lives, day, year, 100 years, a billion years. All right, so just the opposite is going to happen from the perspective of a person who's traveling near the light speed. All right, so if you could just watch this on TV, that's what's going to happen. So that's one way of looking at it, but that's not the only way. All right, so let's summarize special relativity. Einstein said nothing travels at or faster than the speed of light. The only thing that travels at the light speed is going to be light itself. Okay, this is the only one that needed adjustments. Adjustment is that nothing with mass can travel at the light speed or faster. All right, nothing with mass can travel at the light speed or faster. Light is the only thing that travels at the light speed. Time dilates in the reference frame of the traveler at their relativistic speeds, which means that the time is going to slow down when you start to approach the light speed. Time is going to slow down as you start to approach the light speed relative to a non-moving reference frame, inertial reference frame, like an earthbound reference frame. Space contracts in the direction of motion outside of your reference frame. In your reference frame, nothing is going to happen. Space contracts in the direction of motion, along the direction of motion outside of your reference frame. Lastly, the mass is a form of energy.